Well, thank you for coming to today's seminar, and we're about to start. Please be aware of the exit signs before we begin, in case we need to leave the room on short notice. Those that are on the internet, we strongly encourage you for the Q&A to send in your questions at first opportunity so we have time to take it on the air. With that,
thank you. Hi, everyone. Thank you for joining us today for this research seminar on the study Life Cycle Assessment and Co-Benefits of Cool Pavements. My name is Maggie Witt, and I'm the research contract manager for this project. I manage research projects related to sustainable communities, which falls into the categories that are shown up here on the slide. Today, you'll hear from Drs. Ronan Levinson and John Harvey on research that falls into the last category, cool communities. Ronan and John represent a team of researchers that worked on this project from Lawrence Berkeley National Lab, UC Davis, the University of Southern California, and ThinkStep, Inc. The impetus for us pursuing this research project was to develop tools that could be used to aid in decision-making about pavement systems that are built and maintained throughout California. In particular, we hoped to provide information and tools that local governments could use as they make decisions about the construction and maintenance of local roads, parking lots, etc. But obviously, this project has broad relevance in a state like ours that has many roads and paved surfaces that run the gamut, from wide multi-lane freeways to small local avenues. As you'll hear today, there are many complicated factors that can be and are considered in the completion of life cycle assessment, or LCAs. Pavement LCAs is no exception. You will hear that in some cases, pavements referred to as cool pavements because they reflect more sunlight than is typical may actually have a bigger carbon footprint than the conventional alternative. Nonetheless, cool pavements remain a useful tool to reduce the urban heat island effect, particularly in communities that experience very high temperatures during the summer months. Hopefully the illustrations and examples that John and Ronan will provide will help you understand the ins and outs of this pavement LCA and how this tool was created. And I hope that you'll engage with them with questions to help guide your understanding after we've heard the presentations. So with that, I'm pleased to introduce our two researchers. I'll give a short bios for both. Dr. Levinson is a staff scientist and leader of the Heat Island Group at the Lawrence Berkeley National Laboratory in Berkeley, California. With his research portfolio, he develops cool roof, wall, and pavement materials, improves methods for the measurement of solar reflectance, and quantifies the energy and environmental benefits of cool surfaces. He holds a BS in engineering physics from Cornell and a graduate degrees from UC Berkeley. Dr. John Harvey is a professor of civil engineering at UC Davis and the chair of the Transportation Technology and Policy Graduate Group. Professor Harvey serves as the director of the University of California Pavement Research Center, which has an ongoing Caltrans-sponsored project related to the research and development of a wide range of pavement technologies. He holds a BS in civil engineering from Oregon State University, and his graduate degrees are from UC Berkeley. Thank you very much for joining us today. I'll hand it over to you for the presentation.
Good afternoon. Thank you very much to the Air Resources Board for having us here to speak. I'm going to talk today, along with my colleague John Harvey, about our project examining the life cycle and co-benefits of cool pavements. This is a team effort. In addition to Berkeley Lab and the University of California at Davis, we have work shown here from the University of Southern California and from ThinkStep. We begin with a why do we care about pavements as part of the cool community solution? Well, pavements are a pretty big part of our cities. If you were to look at a city from above and go count all the pixels that you find in an image, you would find that change the global warming potential. For example, how much carbon is emitted through building energy use or in the manufacture and construction of pavements. It can change the local air temperature if you have a
Where? Hello? Can you hear this? Yes. Okay.
all right.
Try that. That's fine. Thank you.
All right, I'm going to back up a little bit on the assumption that nobody heard anything. But that's okay. I think of it as a fresh start. Assuming the universe can hear me now, I'm going to begin again. Today I'm going to speak about life cycle assessment and co-benefits of cool pavements. And this is a multi-party effort from Lawrence Berkeley National Laboratory, from the UC Pavement Research Center at the University of California, Davis, from the University of Southern California, and from ThinkStep Incorporated, formerly PE International. Why do we think about pavements as possible cool community measures, cool pavements in particular? Well, if you were to look at the city from above, you'll find that a large fraction of the surface or the urban fabric is paved. It's typically about a third, and the example that I'm showing here for where we are now, Sacramento, a pixel by pixel count, which I don't recommend to you, frankly, it's very tedious, leads you to the conclusion that when seen from above the tree canopy, pavements represent about 40% of the urban surface. Which means that if you're thinking about what can we control, well, pavements are a pretty good candidate. Pavements as warm surfaces usually aggravate what we call the urban heat island effect. The urban heat island effect is the difference in air temperature between the city and the temperature of the air outside the city. Usually cities are warmer than the countryside. And this is because pavements are typically dark and dry, which leads them to absorb sunlight and not evaporate very much water. One approach that you could take is wet pavements, but that's not the kind of cool pavement that we're talking about today. The kind of cool pavement under discussion is the reflective pavement, one that rejects a higher fraction of the sunlight that strikes it. On the left side, I'm showing a typical warm pavement that might reflect 10% of incoming sunlight and therefore absorbs 90%. A lighter colored or otherwise engineered cool pavement could reflect 40% of the sunlight, absorbing only 60%. Of course, you could have many different possible reflectances. And by absorbing less sunlight, it stays cooler in the sun. It also convects less heat into the air of the city, and that is helpful. There are many possible consequences of using cool pavements. One is you modify how much energy is required by buildings for heating, cooling, and lighting. Another is that you change how much energy might be consumed in making the pavements. This will also consequently change the carbon associated with these processes. I mentioned earlier that you're going to convect less heat from the pavement to the air if you have a reflective surface. This is going to lower the outside air temperature. Because the rate at which smog forms is a temperature-dependent reaction, if you can lower the outside air temperature, you'll usually slow the formation of smog. By changing your energy consumption, whether it's in building energy use or in the manufacture of the pavement, you will change the emission of pollutants into the air. All of these are elements of what we call the Pavement Lifecycle Assessment Tool, or PLCA tool for short, after you get tired of saying Pavement Lifecycle Assessment. And this is run over a 50-year analysis period. Our tool can be used for a variety of different purposes. For example, Caltrans can use it particularly to look at the consequences of their pavement material choice, but the primary audience for this tool is decision-making by local governments, which can help them, as I'll show in a later slide, deal with matters like climate adaptation plans, which in fact comes right here. We start with a tool which is designed primarily for city planning, so you can build scenarios of different pavement choices. I will think of using this pavement for rehabilitating my roads, or I will use that pavement. And from the output of the tool, you can make better informed decisions. You can use these results to inform your climate action or your climate adaptation plans. What do we do in a warming world? You can decide whether cool pavements should be something that is promoted by building codes or zoning ordinances. When it's time for maintaining your pavements, you are going to have to choose what to use, and this will give you some indication of whether using a cool material is going to be beneficial. And finally, as you are going to specify the content of your pavement, maybe you're going to say, a cool pavement is something that I would like to do, but I have different choices for cool pavement materials. What should I go for? So these are all part of the decision-making process that we hope will be informed by use of this tool. And now I'm going to bring up John, who will tell you a bit more about the tool scope.
Thank you, Renan. So beginning to look at scope. The first part of the life cycle that we're looking at in the tool, and let me start backing up, just making a few blanket statements. This is what we've kind of agreed as a first order type tool. We have a lot of assumptions in here, many of them driven by the computational time it takes to run one of the climate models drove most of our assumptions. We have a number of other assumptions. And I encourage folks to take a look at the results in the report, the CARB report that's now been published. So looking at the life cycle, we're starting with the first part that we look at is the materials production, transport of the materials, and the construction process. And the construction process primarily has an influence through the burning of fossil fuels to run the construction equipment. Across the life cycle of the 50-year analysis period, we're looking at energy and materials coming into the system in the 50 years and emissions coming out of the system in the 50 years. Materials construction, the use phase is only focused on the building energy part of the use phase here. We're not looking at roughness. We're not looking at some of the other things that we could bring in and which are part of other research. This is focused on building energy for the use phase. We call out end of life and maintenance in the life cycle shown here. In reality, because of constraints of the climate modeling, the assumption here is that whatever we do, we repeat. So if we're doing a maintenance, we assume that for the 50 years, we're going to keep repeating the maintenance. We look at rehabilitation the same way. That's not in reality how we do things, but again, the assumptions still allow us to provide a first order idea of how the tool works and what the results are. So some of the things that could have been included, maybe they're included in other research and tools. They can be considered for the purposes either because of constraint or because a priori look indicated that they wouldn't be very significant compared to the amount of effort and the complexity of bringing them into the tool. They weren't included. So these include work zone traffic delay, not that as big an issue for local government, which is the primary audience for the use of this tool as opposed to state highways. We took a look at carbonation, looked at the literature. Carbonation is where the concrete that's been removed reabsorbs CO2 back into the material and produces a carbonate. Looking at the amount long-term, if you were able to put that in stockpiles and run the carbonation process, plus generally in California, we don't let materials sit in a stockpile for very long. That was excluded. Again, in a more detailed analysis, second order, that could be brought in. Vehicle-road interaction, we're not looking at pavement-vehicle interaction in terms of roughness in this model. We're not looking at stormwater effects, just air pollution, energy and greenhouse gas. We're not looking at changes in equipment. We're not looking at construction equipment changing tier, what are we, tier 4 now? We're not looking at tier 5, tier 6 because we don't have that information and because construction is generally a fairly small part of the emissions. And we're not looking at global cooling. We are going to present a result, an initial result, just for comparison purposes. At this point, global cooling is the hardscapes, as Ronen was talking about, reflecting the energy back up into the atmosphere. And he'll go into some more detail on that later. So those were excluded. And I'm going to pass this back to Ronen to keep going.
Thanks, John. Now hear from me for a while. We thought it would help if we were to give you a little map that breaks down the different consequences of pavement albedo for building energy use and for emissions. I'm going to add some arrows here to talk first about the indirect effect. As you, say, raise the albedo of pavement, you will lower the outside air temperature because you're convecting less heat from pavement to air. As you lower the outside air temperature, one thing that you'll do is you're going to change the need for cooling energy in the cooling season and heating energy in the heating season by the building. You will also change the rate at which smog forms from the precursors in the air. And the change in the building's cooling and heating energy uses will, of course, affect not only your overall energy use, but emissions from power plants, and as something that we didn't mark here, emissions from the building itself, say from burning gas in a furnace. There's also a direct effect from changing pavement albedo. As I make the pavement more reflective, I'm going to bounce more sunlight to the envelope of the building, that is to strike the walls and enter through the windows. This is going to change, again, my need for heating and cooling energy in the building. Sending more sunlight into the windows can also change the need for artificial lighting in the building. And these two collectively will again change the energy use of the building and emissions from power plants and from, say, the furnace. And that is the direct effect. I'll give you a little look into the tool that we designed. It's pretty simple to operate. The user will specify one of roughly 30 cities in California that can be addressed. The fraction of the total pavement in the city to modify, say 30%, and then provide two different pavement designs to compare, perhaps a typical pavement design and some less typical or cool pavement design. But really, it can be any pair of pavement scenarios. These are the inputs to our tool, and we have a number of outputs. Some are evaluated over the 50-year analysis period, for example, the global warming potential, which in other circles would simply be called the carbon dioxide equivalent, the energy use, the criteria air pollutants, things like PM 2.5 or smog potential. The local air temperature, how is that changed? And the local air quality as indicated by changes to the concentration of ozone. I'm going to start with a zoomed out picture of the tool and then zoom in on some subsequent slides, so there's no need to squint at this time. But so you can have an overview of what the whole thing looks like. In one portion of it, we specify the city, and we'll get back some information about the city once it's specified. In another portion, we define the two pavement scenarios, an A and a B. Down at the bottom, we have some outputs that automatically update as we change the inputs. And in this upper corner here, we have some controls which allow you to modify the nature of the outputs and also to export the results. I'm going to zoom in a little bit here on some of the inputs. The first thing that you need to do is specify your city. And like I said, there are roughly 30 cities that you can pick from. In this screenshot, we're showing Los Angeles. After the user has specified Los Angeles, we come back with some information about its building climate zone, which is used in energy modeling, the air basin to which the city belongs, which is used in estimations of change in ozone concentration, some information that we get from various records such as the total pavement area in that city, and where it was obtained from a survey performed by the UCPRC team, the total public pavement area in that city. And these are all expressed in useful ways to help you understand what you're working with. The next thing that you would do is you would specify the first of your pavement scenarios called, unexcitingly, A. And within a pavement scenario, you would first pick your surface treatment, basically your paving material. You can specify both upper and lower surface treatments if you have a complex system, or you could just specify an upper surface treatment if there's really only one layer to it. And for each specification, you can put in a pavement albedo. Albedo is the same thing as solar reflectance, ranging from 0 to 1. You can put in any value you want, but we do give you some basic information about typical values of albedo for that type of pavement. You can then enter a service life in the range of 1 to 50 years. That service life, again, has some guidance for it. In this example, you can't quite read it because it falls off the screen, but if you had a thinner conventional asphalt concrete pavement, the guidance would be 2 to 12 years service life, but for thicker ones, it's pretty arbitrary. You also then specify the actual thickness of your pavement. We again put in what we expect is a reasonable range, and we bound it there, but you can put in whatever thickness you want. So the examples that we'll show today are kind of arbitrary. We designed them with guidance from the paving industry, but you could go put in different numbers. The next thing that you would do is go through the same process for pavement scenario B. So again, move your sliders, choose your things from the pull-down menu, and you would probably want at some point to decide how you want your results expressed. You could look at an absolute change, and that's what you think it is. It's not relative to, it's not a fractional change. You could have an absolute change for the whole city. That's the first choice here. Or an absolute change expressed per unit area of pavement that you're changing, which to me is an easier way to think about it. And relative, of course, is just the difference divided by the values in the first scenario. You can graph your results, or you can tabulate your results. You can choose to show the consequences of the direct and indirect effects combined, those that result from changing the air temperature, that's the indirect effect, those that result from the reflection of sunlight to the building, that's the direct effect. Or you could disaggregate it, looking at only one or the other. But no matter how you choose to view it on the screen, if you hit the Save button, you get all of the graphs exported to PDF, and you get a very nice comma-separated value file that has all of your inputs and all of your outputs. So you can see the results in graphical form shown on the top, or in some simple tables on the bottom, or very, very detailed tables if you go to the output files. Let me just review a few of the metrics that are shown. Some of the metrics are for the full 50-year analysis period. Others are annual, and some are instantaneous. The LCA metrics, those that cover the whole life cycle and have the 50-year analysis period, are global warming potential, which again is equivalent carbon dioxide. The next is, got a long name, photochemical ozone creation potential, which we call smog potential for short. That is units of mass of ozone equivalent. Then there's PM 2.5, everybody's favorite. Primary energy demand excluding feedstock energy. I'm going to come back to that in a second. And feedstock energy. A feedstock energy is the energy contained in the material that is not convertible, not usable as fuel. So for example, if your pavement contains asphalt bitumen, but it's serving a structural purpose and you're not going to be able to burn it for fuel, that is the feedstock energy content in your pavement. And John can talk a little bit later about how to decide whether to include or exclude feedstock energy when reporting your primary energy demand. By the way, some of us would call that source energy, so those are synonymous. Now, there are some annual metrics which relate to the building. The site electricity use, and that's for cooling and lighting. Could also be for heating if you had electric heat, but electric heat, say with a heat pump or resistance heat, is not as common. Site gas use, that's strictly for space heating. The outdoor air temperature, this is a city mean value, and the temperature is evaluated near the top of the urban canopy. And the ozone concentration, and that again is a city average evaluated at 3 in the afternoon. Now, I'll introduce part of how we developed the tool. No, I won't. John will.
All right, thank you, Renan. One thing that I would add, a limitation at this point in the tool on the different metrics that Ronan was going through is right now there's no identification. I mean, we know where they're produced generally, but they're assumed to be all produced in the same place. We're not separating out that the asphalt refinery's over here and the cement plant's over here and the aggregates over here and the effects. So we're all the effects together are reported together. Again, a limitation for first order that can get parsed out and understood a little better. So that's part of the development of this as well. So the first thing that we did is we took a look at local government pavement practices just to set a baseline. What are the treatments that are primarily being used and how much and how often? How often does a local government touch a piece of pavement?
Testing, testing. This one
Those of you in the radio audience, can somebody text me and tell me if you can hear me now? Sure what that meant. Oh, okay. Oh, okay. I think we might want to wait just a sec, see if we can get the web folks going. Okay, we got another microphone working here. Let me check if... it's working. Okay, so we're good on this microphone. We're down to our last microphone. Okay.
A computer with the Wi-Fi.
Okay.
This is.
Okay.
You have to speak right into the...
Thank you.
Sorry?
This didn't work.
Okay, I assume radio audience, text me if we're not coming through. Okay. Okay, so we took a look at local government practice, what they're using, and the other part is how often they're using it, i.e., what percentage of the network do they touch in a given year, and we'll show some results from that. Not working? Okay. Okay, the second part, the next step was we took a look at life cycle inventories for California. This means for flows of materials, the amounts of materials that we're using, which are called flows. What are the impacts for each of those different types of materials, as well as the construction and transportation processes. This was also done in terms of the energy sources that are used in California, looking at the various impacts from the electrical and heating, cooling and heating energy sources. I want to mention that the life cycle inventories, 99% of it, we made a few changes after, but were sent out for outside critical review. So we had the a consultant from the Massachusetts Institute of Technology, from Michigan Technical University, and from the Swedish Transportation Administration, who chaired the group, take a look and give us critique on our inventories. Urban climate modeling was done using a WRF model at the University of Southern California. Urban air quality models were put together by Lawrence Berkeley Lab, and building energy modeling was also done by Lawrence Berkeley Laboratory. And we'll give some more details on these as we go. So looking at the pavement management and maintenance practices used by local governments in California, we focused on 8 such cities for intensive results. We did look at some other cities through the statewide League of California Cities and CSAC survey. The cities generally were treating between 1.3 and 6% of their network. Now that's down a little bit, probably because of funding during the 5 years prior to the survey. We hope that comes up some with passage of SB 1. 20% was an outlier for Bakersfield. They use a very low-cost treatment, but they do it a lot. They treat 1/5 of their network every year. The two primary treatments that are being used by the cities are slurry seal, which is a thin spread treatment that seals cracks and restores some friction if that's an issue, but it's primarily there to provide a sealing for the cracks and to seal the surface of the asphalt against oxidation. And then asphalt overlay was the typical longer term treatment that was used. Air Resources Board asked us to base the energy modeling for the electricity based on the 2020 Renewable Portfolio Standard, which is fairly green compared to the rest of the country. If we substituted in the energy mix from Texas or Pennsylvania or Ohio, we would get some somewhat different results. But so that was what was focused on in California. And I want to have a point that's been brought up as a part of another critique we received. This is what we're producing in California, not necessarily what we're using in California. So when we import from other states, that's going to modify this a little bit as well. And the specific materials we used, our inventories are based on California practice, primarily on California practice and some alternatives within each of those for the manufacture, construction, and transportation. Some primary modeling of the processes was developed by UCPRC, and we primarily relied on ThinkStep's Gabby software to develop our indicators. Pass it back to Renan.
Thanks. Now I'll see if I can get the microphone to work. How's that? Okay, excellent. Our colleagues at the University of Southern California modeled the urban climate to understand how changing pavement albedo would affect air temperature. I'm going to show you here a map of California, and on this map, I'm not really sure you can read it at this small scale, but there's some color coding to show low, medium, and high intensity areas of development. And if we take away the topographical part and we simply go to the map that's on the right, we can see the urban fraction shown. So where you see the darker blue patches, that's where you have you have a denser population. The simulations were performed using WRF version 351. And the nature of the simulations was to model the pavement 3 times. First with a base value of 0.1 albedo, Then with a somewhat increased albedo of 0.2, and then with a high value of albedo at 0.5. And this was done in part to check the linearity of the results. You can see a fair bit more detail of the work in our report or in a recent publication. The air quality modeling was done by coupling the changes in air temperature to some relations between ozone concentration and air temperature that were developed in past work. So the USC team reviewed the literature on this and then picked 4 air basins that are shown here in the gold boxes, Sacramento Valley, San Joaquin Valley, South Coast, and the San Francisco Bay Area. And these are ones that all have ozone issues. And the modeled air temperature change at 2 in the afternoon was coupled to a sensitivity to get the change in urban ozone concentration. Moving on to the building energy modeling. First, let me talk a little bit about the building prototypes, and then I'll talk about our methodology. We considered 10 different prototypes. 2 were residential, single-family home and multifamily housing. And residential is really big because it's ballpark 80% of the building stock in a typical city by floor area. But also commercial buildings, offices, retail, restaurants, schools, hotel. The modeling itself is done in Energy Plus 8.5, and we did 2 things. First, in the modeling, we changed the albedo of the pavement surfaces near the building. As you change the albedo of those surfaces, you're going to, as I mentioned before, reflect more sunlight to the walls and to the windows. We also used the climate modeling results from the USC team to modify what are called the weather files that describe the climate in the city. So if the simulations indicated that there was a certain temperature reduction in each hour, then we applied that temperature reduction to the weather files that go into the simulations. So the former was our path to calculate the direct effects, and the latter is how we calculated the indirect effects. We were able to obtain, with help from the Air Resources Board, the assessors data from each county in California, and the assessors classify their buildings into 60-plus types. We then mapped each of those types to one of our 10 prototypes, and you can see here some examples. Medical buildings and offices were both mapped to office. The single-family homes and the multifamily homes were probably the most important by themselves. I mean, collectively, they're almost 90% of the stock in a place like Los Angeles. And one thing that's really interesting is that the kinds of buildings that we often think of as big and important, such as, offices and stores, they're individually big, but they're really not that much of our built area. And I think John gets to introduce some of our case studies.
Okay, so we're trying the lapel mic again. So taking a look, these results are not in the CARB report. We realized they're not in the scope of the CARB report. There is a paper which is shown here which has the results that we're going to be talking about now. We are working on, and this is primarily, it's published in Energy and Building, so there's a little bit more of a building flavor on this report paper. We're working on using the same tool but with an expanded set of cases for pavement, and also bringing in some life cycle cost information into another paper which is being worked on right now. One of the things that we all want to emphasize as a team is that what we're going to show you are some examples, and anyone, including ourselves, can quibble with the choices we made for the inputs to put into these examples. They are reasonable, and I'll explain a little bit of the reasonableness, but the tool, as Ronen was showing you, allows you to choose anything, pretty much. Okay, so these are some examples that we thought were within the ballpark of reasonableness, within the capabilities of the tool, and give us some first order takeaways. So we evaluated 3 pavement scenarios: routine maintenance, rehabilitation, and longer life rehabilitation. The routine maintenance case study, as we talked about from the citywide survey, slurry is the kind of the base case, the most typically used treatment. And one of the examples we took a look at in here was a reflective coating with styrene acrylate as the medium that holds the reflective materials in it. There are other types of reflective coatings. There are chip seals. There are other alternatives. So the alternatives as well that we're going to show you, not just the values we chose for those alternatives, but the alternatives are amongst a wide number of possibilities within the tool. And the tool is definitely expandable. For the rehabilitation and the long life rehabilitation, as we saw from the survey, the most commonly used rehabilitation treatment is asphalt concrete. A few cities actually don't use slurries. They wait until it gets so bad they have to rehab, and they only use asphalt. The alternative that we looked at is called bonded concrete overlay on asphalt. Within the bond, because of the sensitivity to some variable amongst others within the treatment called bonded concrete overlay, we ran 3 scenarios for bonded concrete overlay. We ran bonded concrete overlay with no supplementary cementitious material. SCM is supplementary cementitious material. What we used for that was we looked around and grabbed a very typical local government Portland cement concrete mix design that's being used for pavement in California right now. The low SCM is using about 20% SCM. It has a lower cement content and replacement with SCM, about 20%. This is not very typically being used for local government right now. This is order of magnitude what Caltrans is using on the state highway network. We went to an extreme. It's a real mix with about 50% SCM and a low cement content. And this is a mix being produced in California. We had the environmental product declaration for it. We don't think it's being used for pavement, and this is definitely not the common treatment right now, but we wanted to get an idea of the beginnings of a sensitivity analysis for this. And this tool is intended to allow users to go way beyond what we're going to show in terms of sensitivity analysis. Again, these are just examples. Long life rehab, all we did was thicken it up and make it last longer. So for the routine maintenance, we're looking at the slurry seal. From the data that we had from within California, and as well as some data being done for a federal highways project, any other field measurements that we could get, we did not use laboratory measurements of albedo. A typical albedo in the middle majority of the life of a slurry seal is about 0.1. We picked, this is primarily used on residential streets, and a typical turnover rate might be 7 years. For the reflective coating, the middle part of the life would probably be an albedo of about 0.3. That's an albedo increase of 0.2. And somewhat arbitrarily, because there is no real long-term data for these guys, we picked a service life of 5 just for comparison, 5 years. For the rehabilitation, the base case is the mill and fill asphalt. Typical albedo in the middle of the life, the majority of the life, is about 0.1. Asphalt mill and fill will typically start at about 0.05, 0.06, 0.07. It will age, and towards the end of its life, it might approach 0.15 after 12, 15 years. The middle majority, it's about 0.1. We arbitrarily picked a service life of about 10 years. Now that's pretty short for a residential street. That might be a little long for the thickness that we chose, which was 60 millimeters, about 2.5 inches, probably a bit short for a route that's carrying heavy bus and truck traffic. Because the limitation of the tool is we can only pick one treatment with one thickness for the entire city, this is in the ballpark as kind of an average, and again, this is for demonstration. So the tool then gives you Each time you do it is 6 centimeters, 60 millimeters. If you multiply that and just keep replacing it, which is the limitation of the tool, over 50 years, you're going to have a total thickness of 30 centimeters, 300 millimeters. Now, the tool does truncate for remaining service life, assuming a linear interpolation at the end of the analysis period. If I do a treatment in year 48 and it has a 10-year life, we only take the 2 years and prorate the thickness and the impact for that. Bonded concrete overlay, middle part of the life, the aged albedo is about 0.25, albedo increase of 0.15 over the base case. We assumed a 20-year life for that. In the example we're going to show, 10 centimeters, 4 inches, and so that gives you 25 over the life. The metrics we're going to show you are the global warming potential, primary energy demand without feedstock energy, and the outdoor air temperature. So the two cases we're going to show you that are in the paper are Fresno and Los Angeles, and 30% of the city pavement was modified in these examples. And I think that's where it's supposed to stop, right? Yeah, yeah, that's right. Oh, yeah.
Thanks, John. Is the microphone working?
Yeah.
Excellent, good. It's always exciting in this particular talk. So here I'm showing you some of the air temperature changes in Los Angeles and then in Fresno. Let's start with Los Angeles. I have a set of 4 bars at 2 in the afternoon and 4 more bars at 8 in the evening. And what we can see here is that upon increasing the albedo of the pavement, that is 1/3 of the, 30% of the pavement in the city, by 0.2, you have an air temperature reduction on the order of 1/10 of a degree Celsius. And the temperature reduction is generally greater at night than it is in the afternoon, and that's consistent with other work that has found that urban heat island effects tend to be larger at night than during the day. We can also see that there is some seasonal variation. For example, the nighttime cooling in Los Angeles in the summer is greater than that in the winter. It's all quite complicated as to what is going on, but the factors that come into play include the availability of sunlight, the thickness of the boundary layer of the atmosphere, and a number of other fun factors. If we go to Fresno, we can see that the cooling is on the order of 0.5 of a degree C for the same albedo increase. One of the important results, though, is that these outcomes actually match quite well with the average result found in a survey of about a dozen or so different modeling studies where the albedo of the urban surface was changed. There's a typical rate of nearly 1/10 of a degree Celsius reduction for a 0.1 increase in the albedo of the whole city, the urban albedo. But in this case, what we're doing is we are increasing by 0.2 the albedo of 30% of the pavement, which itself is only some fraction, maybe like 1/3 of the total area of the land area of the city. In fact, in Los Angeles, the pavement represents something like 7% of the, 30% of the pavement represents something like 7% of the urban land area. So the air temperature reductions that you see here are small because we're applying a pretty modest increase in the reflectance to a very small portion of the city's land area. Now we come to the fun stuff. What did we find out from running these examples with the tool? John mentioned before that there are different stages of the life cycle that we consider. There's the materials and construction stage, which is all about the building and disposal of the pavement, and then there's the use stage, which in this project is scoped to mean the building energy use. I'll show you some examples from our different case studies. This first case study here over on the left, marked 1A, that is using a reflective coating instead of a slurry seal for maintenance. We have 3 columns. The first column in green on the far left, that's materials and construction. And what we see here is that over the 50-year analysis period, the primary energy demand or source energy consumption has increased because there is simply more energy involved in making the reflective coating than in making the slurry seal. The building energy use has gone down because the reflective coating stays cooler, and that has the effect of saving cooling energy. It also has a heating energy penalty, but the cooling energy savings exceeds the heating energy penalty in this example. And if we look at the third column here, well, that's the combined result. So you can see that substituting a reflective coating for a slurry seal for maintenance in this example run for Los Angeles has increased the life cycle energy use. In the second group, we have 3 cases of pavement rehabilitation. In each of those cases, as John said, the base case is mill and fill asphalt concrete, very typical practice. And the comparison case is a bonded concrete on asphalt, and that is shown in 3 versions. The first one here is just very conventional cement concrete. The next one has those low levels of supplementary cementitious materials. And the third is a very aggressive use of SCM. Well, in all 3 cases, the building energy use is the same because the change in the reflectance of the pavement is the same in all 3. But the energy that is involved in the materials and construction is quite different, even though they are all BCOA. In the first one, which is using as the binder ordinary Portland cement, you see a big jump in how much energy is required over the 50-year life cycle for materials and construction. If we go to the case that uses low levels of SCM and removes some of the ordinary Portland cement, you have a smaller energy penalty. And if you go to that case that uses aggressive high levels of SCM, I don't mean aggressive in a bad way, I'm just saying it's not a common practice right now. There's no actual violence entailed in this. You now see a savings, and that's because you've managed to take out a lot of the energy-intensive cement and use the SCM in its place. If you look at the bottom line, for that no SCM case, you've got a pretty substantial penalty. You have a greatly mitigated energy penalty when you have the low level of SCM, and when you have the high level of SCM, now you have a nice savings over the life cycle. But, whoa, we probably better plug in this computer.
Oh, just a moment.
Water break.
Just a moment.
All right, we're back. The individual numbers can be a little bit hard to digest, and without a point of reference, they might not mean anything. But it's the magnitudes of the bars that I want to call your attention to. If I look in this first case for maintenance, whatever the actual numbers are, what I can see is that the magnitude of the change in energy use in the materials and construction stage is just bigger than what happens in the use stage. If I go to the rehabilitation case, it's the same. Actually, the difference is even more pronounced. If I go to this rehabilitation case in the middle, which uses some SCM, then they become comparable. But the main takeaway is that, unlike with some other cool surface activities, what's happening in making the material can be more important than what's happening in the building energy use phase. We'll come to more of that later. I'm going to speed up a little bit on some of this, but if I look at the changes in the life cycle global warming potential, or carbon dioxide equivalent, I again see that what's happening in the material stage tends to strongly dominate over what is happening in the building energy use stage. And for this substitution of a reflective coating in place of the slurry seal, we have a penalty for GWP. We see the same sort of result for the no or low SCM versions of the bonded concrete overlay. You do get a reduction in GWP once you use a lot of SCM. But again, look at the magnitudes of the bars. And so that just points out that what happens in your materials in construction stage is really quite important. Here's the same two things shown for Fresno. Similar trends in the energy use in Fresno. Bit of a difference for the global warming potential in Fresno in that, while of course what happens for the materials is exactly the same, you have from making the pavement more reflective an increase in the use stage global warming potential when we do this in Fresno. And that's because Fresno has a longer cooling season. More of the building conditioning, meaning cooling and heating energy use, is associated with heating. And we picked a very clean electricity mix per the specification. And this mix is so clean that it's cleaner than natural gas. And so the amount of carbon dioxide equivalent output per unit primary energy of natural gas is actually greater than that per unit of primary energy in this electricity mix. So if this was done for some other state that, as John mentioned, could have a substantially different and likely dirtier electricity mix, you probably would have seen a reduction in GWP in the use stage. Again, everything depends on where you are and what assumptions you make. To return to the point of the importance of looking at the material and construction stage, there are some differences in transport and construction, but mostly it's materials. Here we're looking at the material PED, or source energy use, over 50 years for some of the materials that are considered in these case studies. And over on the left, we have the slurry seal compared to the reflective coating. For the slurry seal, there's about 7 instances over the 50-year period because of what we've assumed for its service life, and there's about 10 instances for the reflective coating. And over those 7.1 instances for the slurry seal, or 10 instances for the reflective coating, you can see that just in the materials alone, there's a lot more energy embodied in the cool pavement than in the less cool pavement. And if we go to those rehabilitation cases, particularly because we're not including feedstock energy in these graphs, yes, there's energy that's embodied in the asphalt concrete, but there's substantially more energy embodied in the conventional cement concrete. That increase, that augmentation goes down somewhat as you start adding SCM. And as you have a lot of SCM, you actually have less in the cool treatment than in the conventional treatment. But this is just one way of understanding what's driving all of this. You look at what happens in the materials component. You have a very similar result if you look at the carbon dioxide equivalent instead of the energy over the 50 years. So we can see here that there's a lot more carbon embodied in the reflective coating than in the slurry seal. And you have, for the first 2 cases of using no or low levels of SCM in the cement concrete, increases in the GWP. You get a tiny, tiny decrease when you go to high levels of SCM. They're pretty much comparable. But again, it comes down to what was going on with the materials. That's still me. Now, because we mentioned city planning before, here is how you might take some of these results into your decisions that are being made on behalf of a city. Los Angeles has its own greenhouse gas emission targets, and in 2025, their target for the city is emission of 20 megatons of CO2 equivalent. Now, we can look at the increase in annual CO2 emission over the city of Los Angeles from the scenarios that we've described. In each case, we're looking at increasing the albedo of 30% of the city's pavement. And for the reflective coating, you have a penalty. For the first two cases of the bonded concrete on asphalt, you have penalties. For that third case with a lot of SCM, you've got a savings. And if you compare those annual penalties or savings to the annual target, you can see that over the space of the city, that change ranges from a savings of a 0.03% to a penalty of about 0.5%. So that says that with the existing technologies, you're not likely to see a substantial advancement of towards meeting the greenhouse gas emission targets of the city of Los Angeles. But it isn't all gloom and doom. There's another benefit from making surfaces more reflective, and these surfaces include pavements. As you make a surface more reflective and more of the sunlight is rejected skyward, about 80% of sunlight that you can reflect from a terrestrial surface will reach space without being absorbed or scattered by the atmosphere. And that reduces the temperature of the atmosphere because you're allowing some of the incoming sunlight to escape the Earth's system. This is a very small atmospheric temperature reduction, but since about 2009 or so, people have been looking at, well, how much would you have to reduce the greenhouse gas content of the atmosphere to get the same reduction in atmospheric temperature? And then, given that roughly half of the greenhouse gases that are emitted from terrestrial sources actually stay in the atmosphere, what reduction in emissions would that temperature decrease correspond to? And that reduction in emissions is what we call the global cooling offset. And in each of these cases, I've drawn three columns. The first column on the left, the green one, is the one-time offset that you get from making the surface more reflective. I call it a one-time offset because when you make the surface more reflective, you immediately cool the atmosphere, but you need to keep the surface reflective. If the surface were to return to its original reflectance, you would find that benefit has gone away because the atmosphere has gotten warmer again. Think of it a little bit like sequestration of carbon. If you sequester carbon by growing a tree, that's great, and as long as the tree remains wood, you've sequestered the carbon. If you burn the tree, the carbon is back in play in the atmosphere. So same thing here. It's a one-time benefit, not an annual stream. But we compared this one-time benefit to the 50-year penalties or savings associated with the materials and construction and the building energy use for pavements. And what we see is that the global cooling benefit, which again is a one-time benefit, not an annual stream, is substantially larger than the 50-year life cycle penalties that we see in this middle column for LA, and almost the same thing for Fresno on the left column. Similarly, we see for the rehabilitation cases that the magnitude of this one-time offset always exceeds, and sometimes substantially exceeds, the 50-year penalty or savings. Why does this matter? Well, one of the things that we wanted to look at is it possible that this one-time offset is going to be dwarfed by even the 50-year consequences of changing the pavement? And the answer is it's not. You can't do arithmetic on this. You can't say add a one-time value to a 50-year value. But if you're thinking about a framework of what happens over 50 years or 100 years, and you're looking at this case here where we were choosing a different maintenance treatment, well, even over 50 years, 100 years, 200 years, still the penalty associated with the pavement construction and the building energy use is actually still substantially smaller than the offset. I'm not in any way saying this is the only basis on which you should be making decisions, but it is part of what should be considered. Oh, and by the way, so these rates come from the fifth assessment report of the IPCC. Finally, let me talk a little bit about the value of the energy cost savings. This project is not scoped to do a life cycle cost analysis. However, since we are evaluating the site energy savings and penalties, we can, just by applying energy prices, turn that into energy cost savings. If we look at that first case where we're choosing a reflective coating instead of a slurry seal and increasing the albedo of the modified pavement by 0.2, in Los Angeles, that will give you an annual energy savings per square meter of pavement that you modify of about 3 cents. If you look instead at using a cool roof in Los Angeles, and you think about increasing the albedo of an LA roof by 0.35, which is a more typical sort of value that you would have as an increase for the albedo of a roof, there, the energy cost savings per year are more like 47 cents per square meter, which is 15 times the savings that you get from making the pavement more reflective. So my point here is that because the building energy use savings that you get from a cooled pavement stem from the indirect effect, with in fact some diminishment of those savings because of the stem from the indirect effect with some diminishment of those savings that result from the direct effect, you have a much smaller annual energy cost savings from a cool pavement than you do from a cool roof. And now I'll turn it back to John for some conclusions.
All right, thank you. So some key takeaways, and again, this is from this limited set of case studies which primarily were demonstrating the tool, but do reflect some ideas for choices. In the use stage, the energy demand decreases for the cooler alternative compared to the current alternative in both LA and Fresno, and the global warming decreases in LA but increases in Fresno. Again, relatively small changes either direction for both cases and both parameters. In the materials and construction stage, primary energy demand and global warming generally increase with the cooler pavement alternative. As Ronen was emphasizing, the materials changes and construction changes, which is primarily materials, are generally much greater than the use stage changes when we're looking at the building energy changes. So what this is saying is that focusing on what we do with materials, and we only showed one sensitivity in this analysis, which was changing our concrete mix designs. We can do some things with the asphalt mix designs. We can change the chip seal mix designs. We have some other alternatives. But one thing I also want to add to that, within a given alternative, somewhat arbitrary. For now. We somewhat arbitrarily picked thicknesses and design lives. We definitely know that materials design, as we showed, but also construction quality, good design, good pavement management, putting the right treatment in the right place at the right time is very important. And for any of these treatments that we showed you here, we can potentially have or double the lives, which have or double the energy and greenhouse gas effects through what we do through pavement engineering and pavement management in these cities. So we only showed one example of the kinds of things that you can do to impact the impacts. That's redundant, but change the impacts. Okay, overall with cool pavement, for the scenarios we looked at, which were somewhat typical, primary energy and global warming tended to rise as we went to the cool pavement alternative. Those 50-year global warming changes were less than or considerably less than the one-time global cooling, global warming offset that Ronan was explaining with the surface at basically acting as a reflective surface. I always think of it in terms of an urban Arctic ice shield. Looking at, as I was just talking about, looking at our materials, that and what we directly control in the shorter term is the materials that we put down and our construction quality and what kind of life that we get out of those. Again, one of the things about everything that we did here is it assumes instantaneous change for the entire portion that we're doing, whereas we know we don't touch the entire network, we touch 5, maybe that will go up to 10%, we hope, under SB1 with the higher transportation funding. So kind of the bottom line, and this is somewhat equivocal, but we think that's a key takeaway. If coal pavements reduce global warming, and we saw that that's sensitive to how we do it, and they are found to be cost effective, and the scope in the paper at this point for the building focused on the cost effectiveness from a building energy cost point of view, we know that all of these alternatives have pretty extreme price volatility between the alternatives, and there's a lot of research being done at MIT. We're looking at that 30 years of price volatility between them, and one time one alternative gets much cheaper, one time the other one, and they move by forces which are beyond any of our control in this state or in this room. So we're going to take a look at that and begin to get an idea. But if when and where they are found to be cost effective relative to other strategies, then we think further work is warranted in the development of these technologies. In the end, in the end, we have an infinite number of things that we can try for global warming. Personal opinion here, I think this has been discussed with the team to some degree. What we're really trying to do is create a much more data-rich environment for decision making, and it needs to include the variability and changes that can occur, probabilities of different things occurring, and then we line up how much impact we can have and how much it costs within our fixed budget, or how much we want to change and how much we're willing to pay for that, and prioritize based on how much we can change things and how much it costs to arrive at the best strategies to put together. So the idea here is to provide first cut tools, the first ever first cut tools for looking at urban cool pavement implementation. René?
Thank you. So just some things that you can use. You can go to the project website on the Air Resources Board server, and you can go download our report. And if you get our report, you can find within the report the instructions that are needed to obtain our tool. You can read more about the case studies that we presented in the journal article. And we're also, we've put a preprint of this article available on a website at LBL, and sooner or later we'll hope to have a link that will point from the ARB site to our site, so you can get to it in case you don't have access otherwise. There's a slew of other publications that have come out of this project, and you might be interested to read more about the work that's been led by Mel Pomerantz. We took a very bottom-up approach to analyzing this question. He took a top-down approach. It's a microphone apocalypse. Either that, or this research has broken every microphone in this room in turn, and there are like 6 of them. Just to finish up here, Mel took a very different approach to this problem. He looked at the hourly electricity use consumed in cities for the entire city, related that electricity use to air temperature, figured out what portion of that electricity use represents demand for air conditioning, and taking that approach was able to understand what is the magnitude of the possible indirect cooling energy savings that you can obtain from making your urban surfaces more reflective. So I encourage you to go look at those. Those are the first two publications listed here. If you'd like some very technical detail about how some of the modeling work was done, please look at the last two papers listed. And thank you very much.
We can take questions in here, and if you want to summarize your question, and I can speak it into the microphone for the webcast participants. Or yeah, come up. Go ahead, Bill. Yeah.
Renan is our programmer.
So we just got a comment that it was a very user-friendly tool and also had a lot of comprehensive elements to it, and Bill was generally impressed. I think we did have one question from the web that I'll try to read for us. You can come over and use that one. Okay, so we got one question from a webcast participant that is asking whether or not the group has looked at titanium dioxide. This person says that they're using it as a component in a patented reflective asphalt composition, and some recent data on the possibility that this mineral may actually clean or scrub vehicle emissions and ambient pollution to some degree. So yeah, just a question about if you guys have experience with that.
Hi. The use of titanium dioxide anatase as a photocatalytic material to both keep the surface of a road or a building clean and to remove some of the nitrogen oxides from the atmosphere is something that's studied. I'm aware of an Italian company, I want to say Tally Cement. I might have the name wrong a little bit. They've been doing this for quite a while, and I've read about some demonstration projects in the southern United States. I'd also add that at LBL we're actually we're evaluating the same technology as a building envelope material for cleanliness and for removing air pollution. To clarify something, titanium dioxide rutile, one of the phases of TiO2 is what makes almost every white thing that you see white, with the possible exception of paper and tile. Titanium dioxide anatase is the photocatalytic phase of it. And so we are not in the current work exploring how much adding TiO2 anatase to pavement is going to provide an air or surface cleaning effect. But I have read over the last 5-10 years of a number of studies about this because several companies are making it. So that's what I'll say.
One of the main reflective ingredients in the reflective coating that we were showing is titanium dioxide, and we did get some impacts calculated for us by ThinkStep for those, which primarily the new part was focusing on the environmental impact of mining and processing the titanium. So what would really, for consideration within this type of a tool, what we would need is an environmental product declaration that talked about the materials, and then materials and construction, and then that could be combined with any models that were available for mitigating the pollution. I do know that one other source of work on the University, the Polytechnic of Milano is one of the major groups that's been working on the air pollution side of that. So this tool is actually open well, I don't think the users can load that in, but the tool is built that whatever new materials come up, if we can put together the impacts for it, and we have a good certification for those, any new materials can be included in the framework.
All right, we got another question from webcast participant. Along the lines of cost effectiveness relative to other strategies, it was helpful to have the comparison to other heat island mitigation measures such as cool roofs. However, different measures have different construction costs per unit area. To that end, do you offer in the tool what I would call levelized cost comparison?
Not quite sure what levelized means, but not in the scope is life cycle cost analysis of the pavement alternatives. And actually not in the scope was the building energy cost alternatives. The building cost energy, which Ronen showed, are in the paper, not in the report. That's not in the tool. The life cycle costing is not in the tool. What we recommend I believe it's in the report, I know it's definitely in the paper, is that whatever life cycle cost analysis procedures that the city or the state or anybody is using be used to look at the alternatives, and that gives you your life cycle cost, and you could use a 50-year analysis period, combine those with the 50-year environmental results from the tool, and there you have your bang for the buck, basically the life cycle cost number that you're looking for. Outside of the scope of this tool, I don't think it should be within the scope of this tool. That's kind of a whole big thing. Caltrans has a life cycle cost analysis procedure called Real Cost, which has been customized for California. It's currently being updated, and many cities have life cycle cost analysis procedures that are readily available.
Are there any questions here in the room? Oh, go ahead.
Well, I'm a retired engineer, and anyway, Cal Recycle is looking hard at and sort of promoting the use of tires in pavement and resurfacing. Would this be compatible with what they're looking at or what they're recommending?
So first cut inventories for rubberized asphalt treatments are available in the tool. We just didn't show them in the case study. So you can examine rubberized asphalt. Again, as with anything all of this stuff, if it looks too simple, it probably isn't. Increasing the rubber content decreases the albedo a little bit and will tend to keep that albedo a little bit lower. So rubberized will generally make the pavement somewhat less reflective. On the other hand, our current rubberized asphalt technologies, we generally can get about on the order of the same reflective cracking life, meaning if we put it on in a thin surface treatment on a cracked pavement, and most of our local governments wait till it's cracked until they put the overlay on, we can use about a half thickness or a 60% thickness to get the same cracking life. On the other hand, again, rubberized current technology has more asphalt binder in it, so per ton, it's more carbon intensive. So the tool actually allows you to take a look at these three different things going on: decreased reflectivity, increased carbon content per ton, but likely a longer life for a given thickness, or you can use a reduced thickness for the same life. So, yeah.
This isn't specifically about rubberized pavement, but the point that I would make is that you could use this tool to compare the materials and construction impact of any two pavements that are described in the tool, whether or not you're considering cool community applications or not, which I think is a great thing because you may be thinking about other paths to greenness and So don't worry. You could, if you wish, ignore completely the use phase changes and just focus on the materials and construction stage if that's where your interests lie.
Okay, I think we have time for one more question. I've got one here from webcast participant. So the question here is, do we know how the price of cool pavement products, installation/maintenance, compare to non-cool pavement products? And there's also a second bullet here about the availability of cool pavement products in California, and if their installation and use requires any special equipment, or can any concrete installer easily use the products. So I can repeat parts if you need it.
I've been asked this question a number of times. It depends. There is no such thing as a go to the store and buy a cool pavement technology. There's a huge spectrum within each one. There's a huge spectrum from things that we typically use right now to things that somebody's produced on a laboratory bench and we have no idea how it's going to perform. So I would really back that question. I would say that's not really the right question. And I think would even back up even further and say, are we asking about initial cost or life cycle cost? And I would always really focus on life cycle cost. Otherwise, I think we're going to be penny wise and pound foolish potentially. So all decisions, I think, should be life cycle cost oriented. And there's a variety of things you can do out there. I think the first question of the tool is, do I even get a benefit from this? And it depends on the location. It depends on a number of things. Then the cost is going to depend on not only what you put, but how you put it, the construction quality, the materials that you use, and it can last same thing can last 5 years, same thing can last 25 years, depending on how you design it and put it down. And that's the range from 20% to 200% decrease or increase in environmental impact, depends on just what you did with the thing you're already doing. So I think we should really take a more complex look at a really complex question. And this tool is intended to help to begin to sort that out. So I would say run that, take a look. How easy are they to construct? Can I get them? Again, totally dependent on the location. Do you have contractors that produce that know how to put this down? Is it available within the market in which you're working? Totally depends on where you are in the state.
Okay, thanks everyone. With that, I think we'll wrap up. There was one last little question from that last questioner from online about where to get the tool. So I was going to put back up where you can find it. Oh, there it is. Okay. So here's the summary where you can find it. You can get to it from the report. It's embedded there in the report because there are some steps you have to follow. So we wanted to direct people to how to follow those steps to obtain the tool. So hopefully you will get to use it and try it out, enjoy it, and you can contact me. My contact information is on the research page if you have questions. Thank you.